Thank you for inviting me for giving the keynote and giving the level of the other speakers in the session. It's an honor. I hope I don't disappoint you. So I'm going to talk about the impact of resolution of observed SST climatology and variability. And for those who attended the IGAS last year in Pasadena, this is a wider study at a global scale. There we presented the results for the tropical Atlantic that all began with an undergraduate student work in collaboration with my colleague from Barcelona University in Barcelona, Javier Garcia. He's a climate scientist and also contributor for the IPCC. And then I would like to thank as well to my colleagues at ICM, Aina and Antonio. You may know I don't need to introduce the importance of sea surface temperature in this community, but as you know, this is a key relevant variable for climate, and it's controlling several fluxes and SC interactions. And so during the past decades, mesoscale has been widely studied, but now the new frontier is understanding the submesoscale dynamic and its impact on climate. So that's why here in this community we are pushing and taking a lot of effort to develop high resolution observation of SST, remote and in situ observation both. As you know, some traditional climate-oriented SST observation datasets generally don't include satellite and are typically based on in situ observation. So the main objective of this work was to characterize SST climatology and variability at a global scale and assess the impact of the resolution of satellite observations. And for that, we have intercompared these three data sets. They are ordered from cursor. I think you can see my cursor there. Yeah. So they are ordered from the cursor resolution to the highest spatial resolution. And what is important, I want you to keep in mind, is that, for instance, the ERSST is just taken into account in situ observations. HAT-ISST take both satellite and in situ. And CCI, as you know, is just a satellite. This version is just satellite observation. So and the temporal resolution for these two data sets are monthly. And as you know, the level 4 for CCI SST, it's daily, but we did compute the monthly average to have the same resolution. So the period we have considered is from 1984 to 2016. I know the data set begins two years early, but we just had to consider this because we had a problem, and I just want to give you the right temporal range that we take into account in this study. So I'm going to show you the methodology we have used with this slide. So here we can see the climatology for all the period considered, and this is given at the original grid. So I will always show the cursor resolution first. So this is ERSST. It has 2 degrees, 1 degree, and the CCI, which is the highest spatial resolution. And as you can see, the climatology give us the same kind of information. They are quite similar. Then for SST's anomalies were obtained by subtracting the multi-year climatology from the original data. And here I'm showing you as an example the anomaly obtained for the first year, for 1984. And here the level this is a typo. I just realized a few minutes ago, so it should be degrees. But in any case, as you can here, we just can begin to observe some differences, and especially the spatial resolution. Of course, we resolve better the submesoscale as expected. This is nothing surprising. So the next step is compute the SST anomalies. These anomalies are trended by removing the long-term linear trend. And here I'm showing you the trends that we observe for the 3 data sets for that period. As you can see, We in general have this global warming in all the globe. All of the three data sets detect this the known cold blob here in South Greenland. You can see here. I hope you see. Yeah, I think you are seeing my point. Even if they do have, we do see some differences. They are not that significant, and I will show you just at the end of the presentation. I don't want to make you any spoiler, but we will see that later. So then we have studied the seasonal variability of SST, characterized as the standard deviation of the detrended anomalies. And here you just can begin to see some difference, especially at the high variability region, as the western boundary currents here in the Gulf Stream, and Kuroshio, for instance, and especially here in the Agujas region. So, in order to compute and to compare these three data sets in a quantitative way, what we did was to interpolate the CCI that has a higher spatial resolution to the cursor grid. And for that, we have, and then we did the comparison at a grid point. So on the left, you see the difference on the climatology as an annual mean. And we are showing here the different CCI with respect to ERSST at 2 degrees, and on the right you have the other with respect to the other data set at 1 degree. And as you can see, as a first glance, is that CCI is in general colder than the other two climate-oriented data set, except in the western boundary regions, as you can see easily here. And yeah, I want to highlight here that in all the figures I will be showing today, the solid black lines indicate the statistically significance at 95% confidence level. So we repeated this at a seasonal scale, and the results are robust along all the seasonal cycle. These are the results for all the seasons, meaning DJF, December, January, February, and so on. So this would be March, April. And this is kind of the same for both data sets. This is ERSST, and then for at 1 degree, we have the same results being CCI colder, except in the western boundary regions. So now we do the same with the variability comparison, and here what we are comparing is the variability of CCI minus the ERSST. And what we can see is that in general CCI shows higher interannual variability, and once again, especially in the western boundary currents. And this is robust with the again in all the throughout the seasonal cycle. This is the case for ERSST, and the same, but this is even higher for the case of HAT ISST at 1 degree. So the next step was to see to check and study the ocean-atmosphere interaction. And for that, we have used the ERA5 reanalysis. And here I'm showing on the left, this is the climatology at 2 degrees for the turbulent heat fluxes. And as you know, the turbulent heat fluxes is the composition of the latent heat fluxes and sensible heat fluxes. The latent component is the one contributing most, as you can see here in the amplitude to the turbulent heat fluxes. And we can say that this is due to humidity. And here I want to highlight that we have considered turbulent heat fluxes and both fluxes being positive upwards. That means from the ocean to the atmosphere. Yeah, so for the sensible heat flux, which is mainly driven by, this is driven for humidity, and as you know, mostly ocean is mostly more humid than atmosphere, or almost always. This is why it's mostly positive. And for the sensible fluxes, is driven by temperature, and we have few cases here in Southern Ocean where we have these negative sensible heat fluxes that are below from 0 to minus 10 here. But as I said here, as we can see, the climatology is higher, that we have higher interaction and higher turbulent fluxes in the world's boundary current. So this is on the left now, the variability of the turbulent heat fluxes. And as you can see, this kind of a structure is kind of the same as the one that we saw in the difference, except in the Pacific, the El Nino region, where we didn't have, if you may recall, we didn't have the this difference in you have here. I just put it here as a reminder that in the El Nino region, we don't have this significant difference in the variability. So our question, what we want to find out, if this higher variability in CCI dataset implies higher ocean atmosphere interaction. And for doing that, we have computed, we did the same with the turbulent heat fluxes, we did the same methodology, and we computed the anomalies, the trended anomalies for the turbulent heat fluxes. And we have computed the correlation between SST and turbulent heat flux, heat fluxes, the trended anomalies, sorry. And so here I'm showing the correlation going in blue. It's the negative correlation going from -1 to 1, and the red. And to give you some physical explanation of what does it mean, the red colors here in the correlation would mean, so it's positive correlation, and it means that the ocean is driving the fluxes. And it can happen here. So we have a turbulent heat flux in that region, and you have an anomaly. I mean, the red, it's a warm anomaly from the SST, so we have a positive correlation, but you can, and here the ocean is warming the atmosphere, and in that case, it's the ocean that is cooling the atmosphere. So you can have these two, and it will give you a positive correlation. So this is just to keep in mind that in most of the, as you can see in the results, in most of the regions, ocean is the driving for heat fluxes. So once again, what we did was to try to compute the differences, and to compute the difference of the correlation we did obtain between CCI and IST. And that it's, once again, we do have higher interactions in the regions that where we obtain a higher variability. So this is quite quite surprising, and it's quite robust. In both data sets at 1 degree for the height IST, it's the same. And when we compute the seasonal analysis, it's again robust, and we detect the same behavior. So this will be the seasonal difference of correlations between CCI and IST for 2 degrees. And in the case for height IST, at 1 degree, it's exactly the same, and we are obtaining a really high difference and significant difference in the correlations. And yeah, and last but not least, I think I'm having plenty of time for for comments and discussion. But as I promised you, here I'm showing you the differences. This is the trend at CCIs, and we are going to see that they don't have, this is the difference, and mostly they are not significant trend differences, what means that all data sets represent the same forcing signal. And so for wrapping up and concluding, we have seen that the performance of the three data sets analyzed in this study show similar large-scale patterns for climatology and variability, but they display consistent difference along the seasonal cycle, with CCI displaying more expansive and larger variability, especially in the western boundary regions. The difference in climatology are less apparent, but CCI is systematically colder than the other two climate-oriented data sets, except in the, once more, in the western boundary regions. So we have seen that this higher variability in the CCI dataset translates into a higher ocean-atmosphere interactions. And our results are relevant for climate studies, since the datasets typically used in these studies may have been underestimating SST variability. And this is all from my side. I think we have plenty of time for discussions. That's it. Thank you very much for your attention.
Thank you, Cristina, very promising. There's any questions online or present? There's plenty of time. Go ahead.
So you mentioned warmer SSTs in the CCI in the western boundary currents. Why do you think that is?
That's a good point. I think that there is, for me, this is due to the sampling of the data sets. At the end, the satellite is giving us more synoptic and repetitive observation of SST, and I think it's able to really retrieve the high energetic regions, whereas in situ maybe they might have escaped these dynamical regions. I don't know if I don't know, maybe there is anyone in the room that has any other idea that for me would be really interesting. But I guess that is due to the sampling.
I mean, that's the. I mean, like I said, that's the obvious answer. But are you going to get a chance to look into it a little bit? Because I thought, at least, that obviously there was more variability, and that I could accept because of the, with the satellite, you're going to sample an awful lot more, a lot more detail, a lot more resolution. But you seem to imply, unless I misunderstood your plot, that the temperature itself was higher. Is that correct, or am I just misreading?
Let me share again my. So what you are saying is that the temperature, the climatology was higher.
That's what I thought your plot
wasn't. No, it's not higher indeed. Indeed, in the climatology, they are not that big. No, it's not higher. It's colder indeed. Let me. I don't know. I'm sharing. Sorry, I don't know if I'm sharing my screen now. Wait.
Not yet.
Not yet. It's coming. Okay. I cannot share it now. I don't know why. Wait. Now. Sorry. Yeah. Are you seeing the presentation again?
We got that, yeah.
Okay. So what you are saying is that I mean, in the when we compare the climatology, we don't. Yeah, this is higher. In the western region is higher, but for instance, we do have other regions as the Pacific El Niño that we do have higher variability too, and we don't observe this difference. I don't know if you know what I mean. So for the climatology, I think they are kind of giving more or less the same. When we do analyze, we observe that CCI is colder, except in the western boundary currents. But for the variability, we I mean, what I'm trying to say is that the higher variability does not imply the difference in the climatology. This is my point, because the Pacific, the El Nino region has a lot of variability, and there is not that significant difference neither in the climatology, neither in the here in the variability. I don't know if you see my point.
I mean, I guess I do, but the point I was getting is that CCI is warmer in the boundary current.
Yeah.
Warmer. It's not. I mean, I understand why there'd be more variability because it's just observing more data. But I'm wondering if is there a possibility for it to be something like a selection thing due to something like cloud screening? What do we? I don't know. Anyone wants to say something about that?
Not sure. I don't know. Maybe Chris can give some insight on that. But I wouldn't expect, because I don't know if I wouldn't say that it's cloud, because the cloud coverage is kind of I don't know. I think it has to do more with the dynamics. I don't know. I wouldn't expect that this is due to clouds. Chris, what do you think?
Well, my first question, isn't Owen in the room?
Is it what? Yeah, maybe. I don't know. Okay. Owen?
He's been keeping his head down, Chris.
If he's keeping his head down, I'm quite happy to say some things.
I don't see your room, Chris. Sorry. This is why. I know you were online, so that's why.
I haven't seen this before, so yeah, it looks like there's a difference, and we can look at it. And it could be the cloud detection. Yeah.
So my comment would be, we're seeing more variability, and that's a temporal variability.
Yeah,
we can understand that from sampling, but any system that creates an analysis also has a sensitivity to the real SST, which may not be 100%, because whenever you create a climatology, an analysis, you generally have a climatology in the background and so on. So the other possibility is that it's just all variability, spatial and temporal, in the CCI is greater, possibly because the sensitivity to the underlying SST is nearer 100% in both space and time. Or it could be other effects that are unique to Western boundary currents. I'm not particularly sure that I buy the cold core eddy thing, because we've looked at that over the years, and I think that's we've not found that before, but unless that's emerged in the new CCI version, I don't know. So that's my thoughts.
Yeah, I mean, I guess there's another possibility is that in situ data sets might undersample a strong current simply because drifters are not in there long enough to sample it. And if you've got a ship, you may try and get out of it if you're trying to sail in the other direction as well. So I'm wondering if there's that sort of sampling effect could be going on in reverse, so to speak.
Yeah, that's what I was trying to say earlier. Yeah, I think that's the case. And here, and that, as Chris pointed out, we are talking about temporal variability, but somehow I think it's both. I mean, it's temporal and the spatial variability. At the end, the CCI is resolving higher spatial variability too. That when we interpolate to the coarse resolution, somehow it's resolving higher variability too. And so it can be both at the end. Yeah.
I have one quick comments that I think the Western boundary regions, the variability difference is largely dependent on the reconstruction methodology. Like in ERSST and Hadley ISST, in ERSST we're using what we call the empirical orthogonal teleconnection. It's very similar to the UF. And in Hadley ISST, it's called the ROS, or like similar to the UF, a different kind of, but similar to the UF. This UF application in the reconstruction basically may not be able to resolve the SAT variability near the Western boundary current as well as CCI, because CCI has been high resolution at 0.02 or the solution is quite higher. So I think that's basically the difference why.
Mm-hmm. Yeah, but in any case, we need to translate this message to the climate science community that normally they use these two data sets for comparing and for comparing biases in the models. And now that the computational resources and we are beginning to able to resolve the mesoscale and submesoscale in climate models, I mean, this is the message that we need to take into account other observations than the climate oriented.
Any other question online? Maybe? Oh, there's another question. Go ahead.
Yeah, thank you for this presentation. I am using some of this data to evaluate CSIC model, but I don't know the consequence of the data. My question is, if the variability here, the interannual variability or all the variability is just due to the resolution, if the data, the consequence is independent or dependent. Example, if the CSIC assimilate some satellite data or some bias, or it's different, or the independence, how is the degree of the independence of the data?
So in principle, they are kind of independent because this version of CCI is not using microwave. And SST is using satellite, but for microwave, if this is correct. I mean, if the metadata are correct, this is, so I think they are independent in that sense. I don't know if this answers your question.
She asked if that answered your question. Yes, Cristina. Well, if there's no other question, okay, time for a quick one so we can move on. Otherwise, we can take it to the discussion.
Yeah, very quick question. About the coupling with turbulent fluxes. So don't you think it's also affected by the fact that they are not fully independent if you use Area 5 and CCI?
Yeah.
So it might be better to look at like couple model, a different resolution to have a final answer on the coupling. Thanks.
Yeah, indeed, this is something I need to check. I'm not sure that if Area 5 is kind of assimilating CCI. I'm not sure of that, but this is something we need to check. Yeah. And if you have any other suggestion of any other analysis, it would be more than welcome. Thank you.
Yeah, we do use the ESIM-WF NWP to calculate the skin to depth correction and time of day.
Okay. Okay.
But the SST in year 5 is not CCI.
That's what I was thinking, but okay, thank you, Chris.
And
so they are kind of independent. I can trust.
Sure. In the interest of time, we can continue this conversation in the discussion. Seems like there's a lot more to say. Let's move on to our next talk with Ioanna Karagali from the Danish Meteorological Institute. Here you are. So a new global combined SST and IST CDR from 1982 to 2024 for the Copernicus Climate Change Service. Thank you, Ioanna.
Thank you for the introduction. Good afternoon, everyone. This presentation is obviously a very combined effort from many of us at DMI, and it's a task that we ended up having in our hands because of reasons out of our control. So if you are familiar with the previous C3S, Copernicus Climate Change Service, level 4 SST products, they could not be continued or updated for reasons we don't need to discuss now. So we were tasked within Siemens, the Copernicus Marine Service, to produce a new version of the SST C3S product. But within that framework, we actually decided to enlarge the task and provide something new and unique, which is a combined sea surface temperature and ice surface temperature CDR global. And it's not there yet, but you will hear about that further on. So, as I mentioned, the combined effort from a lot of us at DMI, and I will quickly go to the next slide if I can, which I can't. Yes, I can. Oh, what's up? Yeah, so for those of you who were not here yesterday, very briefly, at the Danish Meteorological Institute, we are a production unit for the Copernicus Marine Service, and within that framework, we deliver regional products for the Baltic Sea and for the Arctic Ocean, both level 4 and level 3S, both near real time and as multi-year products. You've got a very condensed slide here with product numbers and what so on, but we have already some expertise in producing regional products for SST and for ice surface temperature, and for that we were tasked with this new product on a global combined sea surface temperature and sea ice surface temperature a climate data record for the Copernicus Climate Change Service now, so it's a bit confusing between C3S and CMEMS, but please bear with me. It's the CDR, the climate data record is going on from 82 to 2022, and this is going to be released by mid-September this year. And we have an intermediate climate data record extension that will cover the years 23 and 24. And it's, as I mentioned, unique because it combines SST and IST, but it's also unique because it combines infrared and passive microwave. And that is due to work from Pia Englist et al. From a recent publication based on our Arctic product, but we have some new advancements there. So briefly talking about the input and the auxiliary data, just for you to get an idea of what this is about. We've got, it's a quite populated figure, sorry about that, but essentially what we have is that we've got ice surface temperatures coming from the ASTI, so AVHRR-based CDR, produced by a combined effort from Met Norway and DMI, and also now part of C3S as the extension. We also have all the ESA CCI version 3 input data. So we are looking at AVHRR, we are looking at ATSRs, and we are also looking at SLSTR. We've got a set of in situ observations, quite an extended set of in situ observations that we use for validation. And these include in situ observations for the SST, drifters, Argo, quite a large data set. But we also use in situ observations of typically 2 meter air temperatures over the Arctic and also whatever we can get for the southern hemisphere to validate our IST component. And we also have given quite a dedicated effort on creating a kind of up-to-date and high-resolution sea ice concentration product that we use to classify open water from marginalized zone and sea ice. And that I'm going to talk about further on. And in the figure, essentially, you see a time extension of each of the data sets and what period does it cover. Very quickly, a schematic overview of the methodology, and this is somehow similar to what I've shown yesterday for those of you who followed that presentation. So essentially, we've got level 2 and level 3 uncollated input data. We also have a series of sea ice concentration products as input and our landmass, and this is comprising of all of our input data. We pre-process our SST-IST data to level 3, and we also process the sea ice concentration products to an optimal interpolated sea ice concentration mask. which along with the land mask makes our surface mask. Then we do an optimal interpolation using the previous day's guess field. And then we also we produce the level 4 SST-IST combined product. And we also provide an uncertainty. And for consistency purposes with the previous versions of a similar dataset, we will also be providing a different variable, which is going to be only SST, so no IST, for the users that had that already, that they were used on that. And over IST, we will be producing using a sub-ICE SST. But there's going to be discussion about that later on as well. So related to the dedicated sea ice concentration product we are using, it's based on the CARA2 developments, and CARA2 is the Copernicus Arctic Regional Reanalysis, the second version of it, and it's a pan-Arctic product, sea ice concentration product, that is a combination of various OCSAF, sea ice, CCI, and AMSAR2 products. Also SSMIS. It is developed for the Northern Hemisphere for CARA2, but for this purpose, we also extend it to the Southern Hemisphere. And there is a dedicated poster about this product by Ida Olsen et al. On Science Session 3. I'm not sure when I think it's Thursday, but I'm not sure about that, but Thursday? Tomorrow, sorry. And here you just see an example from that poster where essentially it shows different sea ice concentration products versus ESA CCI SST temperatures for June 2007 before applying filtering criteria in the top panel and after applying filtering criteria in the bottom. Essentially, the main interest is for the cases where we've got high SSTs, like you can see up here, and we also have high sea ice concentrations, which are not realistic. And what we do with the extra filtering that is performed is that you can see in the bottom row, we get rid of the sea ice concentrations for warm SSTs. But please go visit the poster. It's available online. It's quite a big effort that has been put into this. Regarding the sub-ice SST, and I know there's been a long discussion this morning, what we have been doing so far is that we have been using the methodology from Banzon et al. 2020, adapting it a bit, and I will explain how. So that paper essentially uses a calculation for the sub-ice SST based on the freezing point temperature using climatological salinity, and this kind of adapted sea ice concentration based on a constant. And that paper has a fixed constant for the entire region of interest. What we've been doing actually is that we have been estimating the coefficient daily to use in this equation. And we use the climatological salinity from the World Ocean Atlas to estimate the sub-ice SST. And we do that separately for the Northern Hemisphere and the Southern Hemisphere. And essentially what this plot shows is an example of the estimated temperature using the equation and daily changing constant. That's the blue line. And also the overlaid on that, the yellow line shows the AVHRR temperature for the same day. And this is for sea ice concentrations between 0 and 15%, for which we actually see the larger differences in the constants. And of course, as mentioned earlier, for higher sea ice concentrations, eventually all curves collapse to almost minus 1.8. So this is the methodology we are using for the sub-ice SST. Regarding validation, just a quick overview. As I mentioned earlier, we have quite an extensive list of validation datasets for the SST, drifting buoys, the global tropical moored buoy array, ships of opportunity, Argo, animals. The plots show an example of matchups for a year, 2015, for drifters top and Argo floats bottom. And the complicated part is the ice surface temperature, because there we know we have very few good quality data to validate IST with. And we have been using measurements from ice drifting buoys and mass balance buoys and drifting ice stations, and also the ice bridge flights. And the ice bridge flights are the only real IST, so skin measurement. The others are 2-meter air temperatures where we know and we expect differences to be large. And now to the complicated part. So we have been running over 30 test runs. And the test runs comprise of a single year of tests, and that we've chosen to be 2015. And we have been testing various options regarding the first guess variances, regarding the background correlation and error function, the uncertainties on the input data, the number of observations allowed, the window of looking for observations. And in this table, which is almost impossible to read, I know, but you have access to the slides later on, we are comparing SST with our benchmark, which is the ESA CCI level 4 product. And essentially, we do this for a year, for 2015. What I'm trying to show you here is that wherever there is green, we score better than the CCI product. Wherever there is red, we score worse. And wherever there's white, we score the same. And the main message is that even when we score better or worse, the difference is on the second decimal. So we are pretty much doing the same as the CCI, the previous version of the product over SST. And the other important thing is that the vertical columns are the different test runs we've been performing, and also differences are very small there. So we try to tune as much as we can, but eventually after a point, differences are very small in the changes we make. And this is for the SST component. For the IST component, we don't have a global benchmark, level 4 product to benchmark with, because as I said, this is the first combined SST and IST. We have been looking at 2015 again for the validation. We only have serial buoys for 2015, and you see here a plot of the available buoys for 2015. Actually, this is for more years, but we are looking at only 2015. The only benchmark we can use is our own multi-year Arctic reanalysis product released for the Copernicus Marine Service. And there is a publication for that mentioned here. But essentially, what you see in this table is the score between the buoys and our test runs. And we get quite large differences that we know of and have been reported in the past, but that is because of the difference between skin and 2-meter air temperature. The important thing is that we don't get very large differences among the test runs. Maybe test run 17 scores a bit worse than compared to the others. And as I mentioned, our benchmark is the multi-year product, and the metrics are here for that. It's a minus 2.87 for the mean difference and 3.36 for the standard deviation. But these metrics are for the period 2001-2017, while here we are only looking at 2015. Yes. And another thing we are looking at, because we are providing it, is the uncertainties on our estimation, both on the SST and the IST. But as I mentioned earlier, the IST is very hard to validate anyway, so we are not looking at the IST uncertainties. We are now only looking at the SST uncertainties. And here is an example of how our uncertainty validation looks. It's a typical plot. We are seeing that from other products as well. It's a very consistent way of validating the uncertainties. And what you see in the plot is essentially an estimate, and the estimated uncertainties that we would like to have. And these are the theoretical curves dashed here. And in red, you see the mean difference and the standard deviation between the level 4 and the in situ. And in the bottom, you have a plot of the number of matchups available. So essentially, what we would like to do is that we would like to go down and go into towards have higher uncertainties approaching the theoretical lines. And we see that we are a bit lower in the uncertainties compared to what we would like to. And this is one of the things we are trying to fine tune in the latest test runs, actually. So in conclusion, what we are trying to create now, and we are about to deliver in a few months, is the first global combined SST and IST climate data record, and also combining infrared and passive microwave observations. It's going to be released on a grid resolution of 0.05 degrees, available from 82 to 2022 as a CDR, with an extension for 23-24 as an intermediate climate data record, so ICDR. We are using a dedicated sea ice concentration product for the sea ice and marginal ice zone classification. The metrics so far indicate that our SST performance is comparable to the previous C3S Global SST product only. Our IST validation so far is similar to the only other benchmark product we have, which is the Arctic SST-IST multi-year product. And as I mentioned, the product is about to be released in September 2024. And you should be looking at both the Copernicus Climate Change Service data store and also CMEMS for the product to be online. Thank you very much for your attention.